This is lecture 16, right? So I will start with a remark. For f is equal to fn, where cn tends to r to n, we have for x belonging to cn, modulus of f of x, or even you can call it as norm r, is equal to norm x, this x, and c is complex, as you all know. Now for x is equal to, here my x is equal to what? a1 plus ib1 up to an plus ibn belongs to cn. And this norm of x is what? Equal to a1 the whole square plus b1 the whole square up to an the whole square plus bn the whole square. So same way, and modulus of this is for this one, okay, this part. Now what is modulus of f of x, or norm of f of x, is equal to modulus of a1 comma b1 comma a2 comma b2 up to n bn. Okay, and this I am going to write it as a square plus b square up to n the whole square plus bn the whole square. So finally you are getting answer of this, and this is same, right? So therefore this is equal to this. Next is Qn of k. Okay, second one. Okay, so this is also the previous lecture, just revising. Recall it. Qn of k is equal to belonging to j ln of k, where array of x comma array of y is equal to inner product of x comma y. So inner product of array of x comma array of y is equal to inner product of x comma y. So matrices in Qn of k are precisely those matrices in Jn of k in which array preserves inner product. So these are the remarks which you all have to know. Next is the proof. Okay, Qn of k is equal to, belongs to Jn of k, where array of x is equal to modulus of array of x. This is modulus, or even you can call it as inner product of array of x, is equal to, not inner product, norm of array of x is equal to norm of x for all x belonging to Kn. In other words, element of Qn of k are precisely those matrices where belongs to Jn of k, such that array preserves the norm. So this is what we have to prove. Okay, we have to show that array preserves the norm. Then, so let us prove. For k is equal to r, first case is what? For k is equal to r, we show that the inner product is completely determined by norm. So take modulus of, or you can say norm. So I'll just say it modulus, okay? X plus y the whole square is equal to inner product of x plus y comma x plus y. Now this x into x, inner product of x into x comma x plus twice this into this, and then this into this, twice this x comma y plus y comma y. Okay, now this is equal to norm of x the whole square plus norm of y the whole square plus twice the real. First I have taken this, then this is this one, and this 2 inner product of x comma y here. Then what I have done is I have taken this the other side here. So in this 1 upon 2 I have plugged it like 1 upon 2. So I have taken all the element of this I have taken the other side. So what half this 1 by 2, if it goes 1 by 2 it will become here, right? So modulus of x plus y the whole square minus, so these terms, this and this, I have taken it the other side. So it is minus modulus of x the whole square, or minus, or you can say inner product, norm or modulus, anything. So minus y the whole square, this. Okay, in the bracket. Next is, hence the inner product is completely determined by norm. Thus, if array preserves norm, then array preserves inner product. You all have to see. Next is, you all have understood this part. See, if RA can preserves the norm, then RA preserves the inner product. So this is from the first part we have proved, right? Such that RA preserves the norm. So we have showed that RA preserves the norm. So this part is done. Now I will be doing the case 2 part, okay? Now case 2 part is what? Next is let K is equal to complex C. Okay? Case 2 part, case 2, okay? Suppose A belongs to Gen of C is such that RA, now this is mapped into Cn into Cn, is a norm preserving, then we can show that rho n of A into this map, it goes from R2n to R2n, okay? This also preserves the norm. So here, if this RA can preserve the norm, then this also can preserve the norm. We have to, okay? So I hope you all understood this part. Then consider for x belonging to Cn. Now I have to consider that x belonging to Cn. Draw the diagram over here of this for roughly to show you all. Cn, this is my R2n. This is again my Cn. So consider for x belonging to Cn. Now modulus of this I have taken, modulus of, I can say even in the product, this thing, norm, okay, whatever it is, so modulus of just r rho n of A into fn of x. So what I have done is r rho n of A into this fn of A, this part, sorry, fn of A. R rho n of A into this I have taken of x is equal to fn into RA of x. So I have just interchanged this, okay, and I have written this as RA of x. So now this is equal to what? Here R was there, now I have to make it in the complex form, right? So this is equal to what? RA of x. See, now this is of complex. Now what I will get, this is RA of x is nothing but x, as RA preserves the norm, as RA preserves the norm, this, okay. I hope you all can see it clearly. Okay, now this is equal to fn of x r. Finally we will get this. So this is like from the how we mapped this part has, like first Cn to Cn, no, that RA thing. In the first, I think we have in the second chapter we have done entire on this, right? So you all can go to it and check. Okay, let me clear this part. So this, you all have to know some definition of this so that you'll come to know this can is written as RA of x. And then because I have to make it C, right? Then this. Okay, I have already told you all. So next is what? Yeah, since fn is bijective. Now my since fn is bijective. Now, okay. R rho n of A into y of r, this R rho n of y is equal to y, this modulus of y, for any y belongs to R to n, okay. Thus we have R rho n of A preserves norm. So thus finally we got that R rho n of A preserves the norm, so that rho n of A belongs to O to n, where A belongs to un. We proved, we showed that R rho n of A also preserves the norm, okay. Next is new topic. So I will be proving one proposition over here. A belongs to Qn of K, then determinant of A, modulus of determinant of A is equal to 1. So this proof, A belongs to Qn of K implies A star is equal to I, which implies nothing but determinant of this A star is equal to determinant of I. Now I have put determinant on both the side of this, and then this is equal to what? 1. Okay. Now this implies, now I will be putting determinant for this determinant of A and determinant of A star, which is equal to 1. This implies what? Determinant of A bar is equal to modulus of determinant of A the whole square is equal to 1, which implies nothing but determinant of A is equal to 1. Okay. So now this is the remark which is given, which you all have to know. Determinant of A star is equal to determinant of A bar. For K is equal to R, A star is equal to A transpose, and determinant of A transpose is equal to determinant of A. So that determinant of A star is equal to determinant of A transpose is equal to determinant of A is equal to determinant of A bar, or conjugate you can say. This is for K is equal to R, okay? And now this is for K is equal to C. We make observation when n is equal to 2. For A is equal to U, V, W, Z belongs to M2 of C. Determinant of A star is equal to determinant of, this is what? U conjugate, W conjugate, or U bar, W bar, you can say V bar, Z bar is equal to, now this into this, U bar into Z bar minus W bar into V bar, and then this, the entire bar you will put, okay, for this, and then you will put determinant of this, the entire this U, V, W, Z, okay, and finally you will get determinant of A bar. So next is, so you all have to know this remark proposition, very important. Okay, next is quaternionic, the quaternionic case, continuation of that part, okay, case follows from the complex case, from the complex case, because for quaternionic matrices determinant of A means determinant of phi n of A and phi n of A star is equal to phi n of A star outside the bracket, okay. Next I will be some remarks now. Remark, the interpretation of the above proposition depends on K. Now first one is what? For K is equal to R if A belongs to O of n, then determinant of A is equal to plus or minus 1. Okay. Second one is what? For K is equal to C if A belongs to Un, then determinant of A is equal to e raised to power of I theta, where theta belongs to 0 comma 2 pi. And third one is for k is equal to h. This is quaternion, h quaternionic group. So if A belongs to SP is what? Symplectic, no? Symplectic group, special symplectic group, something. Then determinant of A is equal to plus or minus 1. We take this without proof, okay? All these conditions, A belongs to SP of N, then determinant of A is plus or minus 1. So you all have to know these remarks very well. Next are the subgroups. Okay, the subgroup this is special orthogonal, no? Now this is equal to what? Set of A belonging to On, where determinant of A is equal to 1. Now this is called the special orthogonal group. Special orthogonal group. So this is called special orthogonal group. The subgroup SU of N, this is special unitary group. So A belongs to UN, where determinant of A is equal to 1. Now this is called the special unitary group. So these are some of the definitions which you all have to know. Next is both. So since both of the special orthogonal group and special unitary group which I have told you all, so both are clearly the subgroups of the general linear group and in fact of the special linear group. S ln of k is equal to this set. A belongs to G ln of k, where determinant of A is equal to 1. Next is the distance between the points. So this is the distance definition or statement, where x is equal to x1, x2 up to xn and y is equal to y1, y2 up to yn in Rn. Okay. Now these two are measured as what? Distance of x comma y is equal to modulus of x minus y, which is equal to, I will write it as root of x1 minus y1 the whole square plus up to plus xn minus yn the whole square. A function f from Rn to Rn is called an isometry if for all x comma y belongs to Rn. So distance of f of x comma y, f of y is equal to, now this distance of this I am going to write it as distance of x comma y. Now this is the proposition, one proof, small one. If A belongs to On, then RA going from Rn to Rn is an isometry. I have to show this, okay. So let A belongs to O of n and x comma y belongs to Rn, okay. First statement. Since it is already given that A belongs to On. And I have to introduce two elements which belongs to Rn. So now distance of Ra of x comma Ra of y is equal to what? Now this I will write in terms of modulus of Ra of x minus Ra of y. So distance formula, how I am going to write it as like this, right? Modulus of x minus y. So same way I have used it here also. So distance of this is equal to this. Next is area of x minus y. Wait. Yeah. Area of x minus y. Okay. So this I have taken area is common. So I have taken it this side, then x minus y. So area of x minus y. Okay. So this I am writing it as modulus of x minus y. Now this is written as distance of x comma y. Why it is like this? Because see, modulus of x minus y is nothing but distance of x comma y. So that's why I got here distance of x comma y. Now this is a rough part, okay? I was supposed to write it here. As A belongs to n implies Ra is norm preserving, okay? Thus Ra is isometry. So I have proved that my Ra is isometry. So next, one last proof and then I am done with this chapter. Next, that if f from Rn to Rn is an isometry with f of 0 is equal to 0 comma then f is equal to Ra for some A belongs to O of n. This is the orthogonal. So in particular, I'm writing the question, okay? In particular, f is linear. So I have to prove this. Is an isometry with this f of 0 is equal to 0, then f is equal to Ra for some E belonging to On. In particular, f is linear. So I have to prove. I want you all to prove this actually. So you all have to prove this, but I will be doing it. But you all also can check and do this proof. So suppose f from Rn to Rn be an isometry with f of 0 is equal to 0, then for any x belonging to R, for any x belonging to Rn, we have so I'll write it this part on the next page, okay? Modulus of f of x is equal to modulus of f of x minus 0. Now this is what? Distance of f of x comma 0. Now this can I write it as distance of f of x comma 0. So now this is distance of f of x comma f of 0. So this I will write it as distance of x comma 0, and this is nothing but modulus of x has f of 0 is equal to 0 and f is isometry. Okay, so next this shows that f is norm preserving. This shows that f is norm preserving but inner products are determined by norms. So f also preserves inner product. That is, I'll write it on. That is, inner product of f of x comma f of y is equal to x comma y. This you all put it as star, okay? I'll keep it as star. Let A be the metric. Let A be the metric whose ith row is of EI. So f of EI is equal to RA of EI for all I is equal to 1, 2 up to n, where my EI is n tuple with next page I'll write it on. Ith entry 1, entry 0. Notice that A belonging to O of n has its rows are orthonormal. Next, I'll write it on the next page. Product of f of ei comma f of ej is equal to inner product of f of ei comma ej. Now this is nothing but what? Delta ij, and this is by the star, which all I have already marked and I have told you all to mark. Okay. Next, this shows that, write down, this shows that f of ei, now this sequence I is equal to 1 to n, is orthonormal. We will, okay, next I'll write it on the next page. We will prove that f is equal to Ra, and thus that f is linear by showing that J is equal to Ra inverse of f is the identity function we cannot directly conclude I'll write on the next page. Conclude, I'll write again, okay? Conclude f is equal to Ra has f is not given to be linear. Now what we'll do is, now we'll take the distance, okay? So distance of g of x comma g of y is equal to what? Now this is equal to what? Distance of Ra inverse of f of x comma Ra inverse of f of y. Now this is equal to distance of f of x comma f of y, right? So what it was? Ra inverse of f of x, Ra inverse of f of y. So I have written it in this form. Now this is equal to what? Distance of x comma y. Okay. So thus G is isometry with G of 0 is equal to 0. So G preserves norms and inner product as above. And I'll write it on the next page. And G of EI is equal to RA inverse of F of EI. This is nothing but what? EI. And this is for all I is equal to 1, 2 up to n. Now let x is equal to Rn, right? X is equal to summation of I is equal to 1 to n AI, EI, and G of x is equal to summation of I is equal to 1 to n BI, EI. Then next is what? BI is equal to inner product of G of x comma G of x comma EI, and this I can write it as inner product of G of x comma G of EI. And this is equal to nothing but x comma EI, and this is nothing but my EI, which proves G of x is equal to x. So G is identity function has required thus f is equal to Ra, and hence f is linear, and hence f is linear. So finally we proved that f is linear. Okay, so G is identity function as required, thus f is equal to Ra, and hence f is linear. So I'll end up my lecture here, and this is the end of the third chapter. If you have not understood this, I want you all to solve, okay? So that's why I have not went in detail. And if you all have not understood any of the topic from this lecture, you all can ask me, you all can comment. Thanks for watching. So